So now we're going to get into triangle similarity. And so what we're going to have to deal with is just some relationships. We'll start off with right triangles, but then we'll get into some other possibilities. The idea here is that if we know what the proportional relationships are within certain triangles, then we'll know whether or not they're similar to one another. I always kind of equate it to the mini-me relationship. So that's a little Easter egg for you. Just tell me the movie. So it's like he's identical to you in every way, just 1/8 your size. So I'll take that as a bonus point. If somebody could identify that Easter egg, the movie that that came from, send me a message on Remind, and I'll give you that point. So what's happening is there are relationships that exist between triangles that, even though they're not necessarily congruent to one another, so equal in measure and angle of angle and sides, then they can still be similar to one another. All right, so have the same characteristics, just be different sizes. All right, so there's a little activity here. You can do it on your own. It involves you just getting a pair of scissors and a ruler and a piece of paper and tracing this figure, cutting it out, and identifying the sides and angles that are in proportion to one another. Right? There are certain angles that should be congruent to one another, so corresponding angles should be congruent. The sides, though, should be in proportion to one another. All right, so I'll give some bonus for that if somebody completes that. If you trace out this diagram, you'll have to trace it out a few times just to kind of get enough triangles to work with. Then cut up each triangle. So you'd have a triangle ABD, the big one. Then you'd have the two smaller ones. And you'll need a couple of sets of each. And if you just put them on tape them or paste them down to a piece of paper and just identify which angles are corresponding congruent and which sides would then be in proportion to one another, I'll commit to 5 bonus points for that. All right, so all you'd have to do is send me a picture of your work. I don't need you to go too crazy with that, but like you make a little chart or poster or something like that. Take a picture of it and send it to me on Remind. All right, but yeah. So I'm just going to kind of cut to the chase, though, because there are relationships that we can rely upon. All you'd be doing for that bonus is really just kind of coming up with visuals for it. So right triangle similarity, the blank drawn from the blank angle of a right triangle divides the triangle into two triangles that are blank to each other and also blank to the original. So a lot of blank. Right, so let's start filling in the blanks. So the altitude. Right, we learned about that term. Oops, a little stray mark there. We learned about that term way back in the beginning when we were defining geometric terminology. The altitude goes from an angle to the opposite side of that angle, forming a right angle. From the right angle of a right triangle divides the triangles into the triangle of the two triangles that are similar to each other and also similar to the original. All right, so and there's some justifications in the form of a diagram, but we also have these ratios, proportions, etc. that come out of all of this. So the first one, I'll just highlight them as we go. AB to AC. So let me skinny up that. AB, so let me just highlight AB to AC. And then AC to AD. All right. So it's basically saying that if I have a ratio of AB, so this long hypotenuse, So this is the hypotenuse. To this leg of the big triangle. That would be in proportion to, and I'll use a highlighter. It's going to be like a double highlight, but still, I'll just put it right there. That's going to be in proportion to, I'll throw a little right angle in here, AC to AD, right? So this leg here, I wrote it on an angle here, becomes, so this is the leg of the big triangle, will now become the hypotenuse of the smaller triangle, right? It serves a dual role. It's two things at the same time. It's a hypotenuse of a smaller triangle, but that hypotenuse also serves as a leg of the larger triangle, right? So that proportion would be a true relationship, right? And we'll go through some examples, because the first time I saw this, I was like, what the hell was that? And if you're feeling the same way, that's not abnormal. All right, so not abnormal is normal. Yep, that's what I wanted to say. All right, so then AB to CB. So the whole shebangity bangity boom here. AB to CB. So a hypotenuse and a leg in proportion to CB. Right, that serves as a hypotenuse, and I'm going to try to highlight it again. Here's another triangle. CB is now a hypotenuse of that triangle. All right, that's going to be in proportion to the corresponding leg of that triangle. All right, which is this guy. All right, now I'm not going to highlight the last one, because you highlight everything, it's like you highlight nothing. AD to CD, CD to DB is also going to be another hypotenuse leg. Oh, actually, in that case, it'll be AD to CD, two legs of a triangle. All right, so leg to leg, congruent to equal to leg to leg. All right. So we're going to look at some examples on the next page that allow us to just kind of flesh this out a little bit. But it's not going to be that difficult, because everything that we touch on is going to fall into one of these three categories. All right, so flipping over. So nothing's labeled. That's the first thing you notice, but they all have the same general structure. So what I'm looking at here, or as what's on the previous page, sometimes don't finish my sentences and get into trouble. All right, so what I'm looking at here is a leg and a leg. All right, so leg, leg. All right. For the other triangle, I also have a leg and a leg. All right, so this pair of legs are going to have dual roles. All right, they serve as the same side, or well, not necessarily the same side, but they're the same length of a side, but they are parts of two different triangles. All right, so what we're looking at here, and I'm just gonna, it's gonna get a little weird, but I'm gonna take this first triangle, I'm gonna pull it out, I'm gonna draw it off on the side here, and I'm gonna label it 7 and X. All right, the other one I'm going to put right next to it. So basically I'm going to draw the two triangles just split. This is X and 9. All right, both of which have right angles. Now, let's see if this app is worth the price I paid. Movie reference? All right, so I'm flipping it over on its side. And now I have the appropriate relationship between the two triangles, because now my corresponding sides should be in proportion. All right. So when we're setting up a proportion, all we're doing is we're taking the corresponding sides and making a ratio out of them, 7 over x. And then x over 9. X over sideways 9. And then when I cross multiply, because when you have a fraction equal to a fraction in order to solve for x, one way to do it would be to cross multiply. There's other ways, but this is the most convenient, at least for this topic. X squared would be equal to 63. All right. Then I'd have to take the square root, and I get x is equal to the square root of 63, which I now have to break up. All right, but let me show you a little nifty trick, something from my years of doing all this. Because if you have to break up the 63 anyway, then it kind of begs the question of why you multiply the 7 and 9 to begin with. So I would write this as x squared is equal to 7 times 9. And then when I take the square root, I take the square root of the whole thing. It becomes x equals the square root of 7 times the square root of 9. Square root of 9 is equal to 3. So we have 3 radical 7. And so that would be my value of x. All right. Now, that's a lot. We want to streamline this. I've done this long enough to know that it can be definitely a little mind-bending if you don't come up with the standardized approach for solving this sort of stuff. So what I do is I just draw just an upside-down T, or if you want a perpendicular symbol. But basically, it's the idea is that those are the relevant pieces of the altitude to the triangle, hypotenuse to the triangle situation. All right. I'm going to label these sides A, B, and C. I'll put my C on the inside. So my rule, because lots of us like rules, A over B is equal to B over C. All right, just a much simpler variation of what we just did without showing all that work. All right, so 7 over x equals x over 9. Simplify, solve, etc. All right. The second problem is pretty much the same thing, except they give us a little extra piece of information. This 25 is telling us that this guy is equal to 16 because of the addition postulate. But basically, if you just recognize number 2 is just a rotated version of number 1, this would be another one of those A over B equals B over C situation. So 9 over x is equal to x over 16, cross multiply. X squared is equal to, like I said before, don't actually multiply to 9 and 16 because we're going to take the square root anyway, and we may have to simplify. All right, so x would be equal to the square root of 9, which is 3. Square root of 16 is 4, 12. All right, so number 3 is pretty much the same idea, so put a little star on that for you. Number 4, it's the same rule again. Actually, 4, 5, and 6 are all the same rule. Just a little bit of a twist on it. All right. Even 7, honestly. So I'll put that there because I'd rather you play around with this first, and then I'll field any questions that come after. It's numbers 9 and 10 that are a little bit different, and that's that hypotenuse leg relationship. Here's my hypotenuse, and here's a leg. All right, so 60 to 36. Then if I'm focusing, it's like one of those brain teaser type images where you see the you know, like you see an old lady in a rocking chair, but if you look at from a different perspective, you see just like a witch's nose or something like that. You know, like this is really all that is. So from one perspective, you know, just focusing in on, I wanted to do that in green. The smaller triangle, I have a hypotenuse and a leg. For the larger triangle, I don't know why it's doing that. For the larger triangle, okay, it doesn't seem to want to let me sketch, so I'm just gonna make it bolder and draw it in. That bad boy. This whole shabiggity bangity boom here is the hypotenuse, and now this guy here is the leg. All right, so now that hypotenuse is the sum of x and 36, with the leg being equal to 60. All right, so still cross multiplying. 36 times, I'll use parentheses here, x plus 36 is equal to 60 times 60. All right, this one actually doesn't have a square root situation going on, so I'm actually going to do the multiplication. 3,600. If I want to get x alone, my next step would be to divide out the 36. So 3,600 divided by 36 is 100. I promised that I would try to keep the algebra to a minimum, and this is me attempting to do that. X would be equal to 64. And all we're looking for here is the value of x, and so mission accomplished. All right. So this is that hypotenuse leg situation. All right. So those are really the three variations, because it could be the other hypotenuse leg combo, but really it's that upside down T or the hypotenuse leg. So it's one of those possibilities. If you can kind of get around those two ideas, then you should be in good shape. More than good shape, great shape. All right, so putting a star on number 9, and there it is.